Hey guys, welcome back to lecture series on Fourier transform. Already I have uploaded plenty of the videos based on the Fourier sine, Fourier cosine and their inverse transform. In my last lecture I explained to you all properties of a Fourier transform. Okay, so if you are interested to see this property, go check in my playlist. Okay, in my today's video I'm gonna explain to you all modulation theorem. Okay, so we go for understanding modulation theorem, okay, from our Fourier transform. Now here it is a statement for our modulation theorem. Statement, it says that if capital F of s, okay, we consider capital F of s as a Fourier transform. Okay, yes, so if capital F of s is the complex Fourier transform of a small f of x, okay, capital F of s is a complex Fourier transform of a small f of x, then we write, okay, then we write f of capital F, that means this one is a Fourier transform over small f of x into cos ax. Now see that before we are taking Fourier transform over only small f of x, but now this property says that what happen if f of x come along with the cos ax, okay, or any other sin x or any other terms, okay. So then we write f of small f of x cos ax as a minus infinity to plus infinity f of x cos ax e raised to isx ds, okay, dx. Yes, now see that we are going to apply Fourier transform on this function, okay, Fourier transform here on this definition of Fourier transform on this function, okay, and we are trying to reduce this term into this one, okay. Yes, so let's get start the solution, okay, proof of this theorem. So we apply a Fourier transform form here for Fourier transform, okay, and a Fourier transform, it can be defined as capital F, okay, capital F over small f of x, okay, capital F over small f of x, it defined as minus infinity to plus infinity, okay, minus infinity to plus infinity small f of x e raised to isx dx, okay. Yes, this one is our definition for Fourier transform. Yes, so we are going to apply this definition for this Fourier transform, okay. So replace small f of x as f of x into cos x, okay. Yes, so f of x into cos x, it also replace here, okay. Yes, let's apply the Fourier transform to our given Fourier transform, okay. So capital F, okay, Fourier transform over small f of x, Fourier transform over small f of x into cos ax, okay. I consider this side as it is here, okay, I consider this side here. So I'm going to apply this one with our Fourier formula for Fourier transform, okay. Yes, so which is a minus infinity to plus infinity integral we have here. So f of x, when f of x it is there, we write f of x, but instead of f of x we have f of x into cos x, so replace f of x as a f of x into cos ax, okay. Now see that whenever we have this f of x, we consider only f of x, okay. Yes, but instead of that f of x we have here f of x into cos x, okay. So we write f of x into cos x instead of f of x here, okay. Yes, and e raised to isx dx, okay. So complete this one under, okay, e raised to isx ds here, okay, dx. Now see that we are going to reduce this one. Observe here, we want this form, we are trying to convert this integral into this one. So f of x it is already there, okay, e raised to isx it is already there, dx it is already there, okay. So we have to reduce the term over here, okay. Yes, so I'm going to reduce this term here. So here in our Fourier transform, the proof of that Fourier transform, we have to show this one here, okay. Yes, that one is the property, standard property for Fourier transform, f of capital F over small f of x into cos x. We have to show that 1/2 f of s plus a plus f of s minus a, okay. So that for definition I applied here, okay. Yes, that definition I written over here. Now see that f of x cos ax can be written as, when we apply Fourier transform, we got this term here, okay. Yes, now see that is one of the easier, don't have anything, okay. So what we do here, we go for expansion of a cos theta, okay, expansion of a cos theta, but it we go for it later on. First of all, you need to understand how I have applied this Fourier transform, okay. So this one is the formula for Fourier transform. So whenever f of x is there, we take f of x. Whenever f of x into cos x is there, we write f of x into cos x. Okay, yes. And one more result, we know that. What is the result for cos theta? Let me write the result for cos theta, that is applicable here. Okay, so cos theta can be written as e raised to I theta plus e raised to minus I theta, e raised to I theta plus e raised to minus I theta divided by 2. Okay, this one is the value for cos theta. Okay, e raised to I theta plus e raised to minus I theta by 2. Or we write more result for sin theta. So just for your reference, okay, take it, note it down. E raised to I theta minus e raised to minus I theta by 2 divided 2y. Okay, these are the two formulas are important here, guys. Okay, so I'm going to apply cos theta, result for cos theta over here. Okay, it's not that difficult, just need to substitute the value. Okay, now see that when we have cos ax, okay, this one is the value for cos theta, but I want cos ax, so cos ax can be written as, now see carefully how I'm going to replace. Okay, yes, so we have the value for cos theta e raised to I theta plus e raised to minus I theta by 2, but instead of a theta we have ax. So wherever you get the theta, replace ax here. So I'm going to write this one, e raised to I times ax plus e raised to minus I times ax, okay, divided by 2. See that how I have written. Okay, it is easier, guys. Okay, I replace theta as ax only, so I form this cos ax as here. Okay, so replace that cos ax in this integral. So I'm going to write the integral over minus infinity to plus infinity. Okay, yes, I'm going to write integral here minus infinity to plus infinity. Okay, f of x we keep as it is, we are not going to do any changes here in f of x. Okay, cos ax, so cos x can be written as e raised to I ax, e raised to I times ax plus e raised to minus I times ax divided by 2. Okay, this one is the value for cos ax, and e raised to I s x dx. Okay, that e raised I s x as it is here, dx as it is here. Okay, so this one is the value for f of x into cos x. Okay, yes, so I got this expansion over here. Okay, now see that e raised to I ax and e raised to I s x. So try to take this term here with this one and e raised to I s x with this one. Okay, so we'll get the exponential term separately. Okay, yes, so what we do, we take 1/2 that constant outside here. That means this complete divided by 2. 2 it is outside, constant it is there now, so we take outside. Minus infinity to plus infinity small f of x. Okay, minus infinity to plus infinity small f of x. Okay, e raised to I ax into e raised to I s x. Okay, that means now see that e raised to I ax multiplied by e raised to I s x. So when base is the same, we add their power. Okay, so we take e raised to I ax plus I s x. Okay, I ax, okay, I ax plus I s x. So as we have the base same, we add their power plus e raised to minus I ax into e raised to I s x. Okay, so add their power. Okay, e raised to minus I ax plus I s x. Okay, so I added their power when we have base same. Okay, yes, so f of x it is also here. Okay, so I multiplied f of x here, f of x here. Okay, e raised to I s x here, e raised to I s x here. 1/2 it is outside here. Okay, so this is entire bracket, and outside of bracket we have integration with respect to dx. Okay, yes, I hope you all have understood. So here we can see that we can take I common from here and x common from here. So remaining term 1/2. Okay, minus infinity to plus infinity. Okay, f of x, a separate integral also. Okay, so take I common, x common, e to the power I common. Okay, it's remaining here a plus s. Okay, a plus s remaining here, and x also common. Okay, so see that this one is similar like Fourier transform form. Okay, yes, dx in here plus. Okay, so 1/2 keep it is outside. Okay, so again apply integral over minus infinity to infinity for this term separately. Okay, yes, so f of x keep as it is here. Okay, so take I common from here and x common from here. Okay, yes, then we write s minus a, okay, s minus a. So I common from here, e raised to I common from here, okay. So s minus a, and x also outside here, x outside here, and dx, okay. So I hope you all have understood what I have done. This is a little adjustment in their powers, okay. Now see that bracket complete, okay. So 1/2. So this entire integral represent Fourier transform over s plus a, okay. Now see that Fourier transform over s plus a can be written as e raised to I times s plus a into x dx, okay. So this entire form represent Fourier transform over s plus a. Again Fourier transform over, now see that s minus a, it is there now, we define s minus a, Fourier transform over s minus a here, okay. I hope you all have understood. This is the expansion for Fourier transform. This one is also expansion for Fourier transform, okay. Yes, and that is the thing, that is the quantity identity we have to prove here, okay. Fourier transform over f of x cos x, okay, can be written as 1/2, okay, f of s plus a into f of s minus a, okay. So this one is our required modulation theorem, okay. So I hope you all have understood. It is one of the easier, guys. We are applying one of only single standard result here, that one cos theta, okay. So remember that cos theta always, okay, which is e raised to I theta plus e raised to minus I theta by 2, okay. Yes, and this one is a Fourier transform for the formula, okay. So we have to prove this side equal to this side, okay. Yes. So for your information, for more reference, you can note it down this my theorem, okay. Yes. So I hope you all have understood my entire solution, okay. So thank you everyone, guys. Thank you for my today's lecture.